In the vast tapestry of human knowledge, there lies a remarkable journey that began with a simple dream. Once it was said, a single mind could grasp all of human understanding. Today, as we stand amidst an explosion of information, we might wonder if such comprehension is still possible. Yet, this story isn't about the quantity of knowledge, but about something far more profound: the quality of understanding. Consider the cosmos that surrounds us, where each discovery reveals not just new facts, but deeper patterns. While we may not be able to memorize every position of every planet, or catalog all 600,000 species of beetles, true understanding doesn't require this. Instead, it seeks the underlying principles that govern reality itself. Through Einstein's general theory of relativity, we gained not just predictions about planetary motions, but insights into the very fabric of space and time. This theory doesn't just tell us what will happen, it reveals why it happens, showing us how space curves and time bends in the cosmic dance of gravity. But here's where our story takes a fascinating turn. Prediction alone, no matter how perfect, isn't enough. Imagine having a magical oracle, capable of predicting any experiment's outcome. Even with such power, we would still need understanding to innovate, to create, to solve new problems. If we wanted to build a spaceship to the stars, the oracle could tell us if our design would work, but couldn't design it for us. Understanding is what bridges the gap between knowing and creating. Through time, we've seen this pattern repeat. Ancient master builders relied on countless rules and traditions, passed down through generations, limiting them to familiar designs. Today's architects, armed with deeper understanding, can create structures those ancients could hardly imagine, from soaring skyscrapers to orbiting space stations. This progress didn't come from accumulating more rules, but from developing unified principles that work everywhere, from Earth to Moon. As our knowledge grows, we witness a profound battle between two forces. On one side, the increasing breadth of what we know pushes us toward specialization. On the other, the deepening unity of our understanding pulls seemingly different things together. Remarkably, depth is winning this battle. Consider how modern mathematics contains within it all the understanding that ancient number systems provided, yet in a clearer, more powerful form. When Copernicus placed the sun at the center of our solar system, he didn't just add another theory, he simplified our entire understanding of the cosmos. When Faraday and Maxwell unified electricity and magnetism, they showed us that apparent differences often mask deeper connections. In medicine, this transformation continues today. Where doctors once relied solely on specific treatments for each disease, they now understand the common molecular mechanisms connecting seemingly different conditions. This deeper understanding allows them to develop new treatments even for conditions they've never encountered before. What we're witnessing is not just the accumulation of knowledge, but its transformation. Like streams flowing into rivers, and rivers into the ocean, our understanding is becoming more unified. We're not moving away from comprehension, but toward it. This doesn't mean we'll soon understand everything there is to know. That's an entirely different matter. Instead, we're approaching a point where the structure of our knowledge itself is becoming more coherent, more interconnected. This journey leads us towards something remarkable, what we might call a true theory of everything. But this isn't just about unifying the forces of physics or understanding particles and waves. It's about something far grander, a unified understanding of reality itself. This theory won't explain every detail of existence, that's beyond reach. But it will show us how all our explanations fit together, how they form a coherent picture of reality. As we look up at the stars, we're not just seeing points of light in the darkness. Through our understanding, we see the complex dance of gravity and space-time, the birth and death of stellar giants, and the fundamental forces that shape our cosmic home. Each new discovery doesn't just add another piece to the puzzle. It helps us see the whole picture more clearly. We stand at a remarkable moment in human understanding, where the depth of our knowledge is beginning to reveal the underlying unity of all things. This isn't the end of discovery, but rather the beginning of a new way of seeing reality itself. As we continue to explore and understand, we're not just gathering more information, we're uncovering the deep connections that bind everything together in the cosmic dance of existence. In this journey toward understanding, we find that knowledge isn't just about accumulating facts, but about seeing the patterns that connect them. Just as space and time are woven together, just as matter and energy are two faces of the same coin, our understanding of reality is revealing itself to be a single, interconnected fabric. Through this lens, the cosmos becomes not just a collection of objects and events, but a coherent story written in the language of mathematics and physics. As we stand here, looking both backward and forward in time, we see that our journey isn't taking us further from understanding, but closer to it. The future holds not just more knowledge, but deeper insight, not just more information, but greater understanding. In this cosmic dance of discovery, we're learning not just about the universe, but about understanding itself. Space, vast and unending, offers mysteries that have bewildered humanity for generations. We have explored only the tiniest fraction of its secrets, yet it holds answers not just to the cosmos, but also to how we make sense of the very universe we inhabit. Science is our greatest tool for unraveling these mysteries, a tool shaped by a profoundly dynamic and iterative process. What propels us forward isn't certainty, but a relentless drive to replace incomplete answers with better ones. Today, we'll explore the wonders of scientific discovery and how it mirrors the very nature of space itself. Scientific discovery is not as straightforward as it may seem. It rarely follows a direct path, instead resembling a vast web of questions, experiments, and theories that constantly evolve over time. A scientific theory often emerges when current explanations fail to account for new observations. Imagine capturing light streaming through the cracks of a closed box. Each discovery is like uncovering a small part of a much larger picture, revealing both answers and new questions simultaneously. The goal of every scientific endeavor is not simply to collect observations. It's to develop better and deeper explanations for what we see, and, critically, what we don't fully understand. When we cultivate knowledge through science, the process echoes the iterative development of theories. It begins with identifying a problem, a gap in our understanding that demands exploration. From here, conjectured solutions or hypotheses are born, each suggesting a new way to explain what we observe. These hypotheses are then subjected to rigorous testing and criticism, where weaker models are discarded in favor of stronger, more robust ones. Paradoxically, this trial and error process often requires backtracking. Progress isn't always linear. This is the very foundation of how we refine and grow knowledge, one puzzle piece at a time. Criticism plays a vital role in this process. Contrary to popular belief, most criticism of scientific theories doesn't stem from experiments, but from direct challenges to the explanations they provide. When a new theory is proposed, it must explain more than the one it replaces. A theory that cannot withstand scrutiny is rejected, often paving the way for better ones to emerge. One critical aspect of this process is that every scientific theory has to be falsifiable. It must expose itself to the risk of being proven wrong. This openness to scrutiny and the elimination of weak ideas are what strengthen the surviving theories, making them not just accurate, but deeply explanatory. Though science often presents itself as rooted in empirical observation, it is not simply about collecting data and extrapolating truths. This idea, known as inductivism, assumes that theories straightforwardly emerge from accumulated observations. However, the reality is more nuanced. Theories originate as conjectures, bold, often unjustified guesses about how things truly work. These initial ideas are then tested and refined, not as a matter of tallying observations, but as a deep commitment to explaining underlying realities. Science, in this sense, is more driven by explanation than prediction. The nature of knowledge itself evolves much like the biological processes seen in nature. Just as species compete in an ecosystem, theories battle for survival in the intellectual landscape. Some are discarded, others adapt, and new ones emerge, better suited to explain the mysteries that eluded their predecessors. This evolutionary nature of knowledge ensures that the strongest theories persist, even while making room for competition and progress. It's trial and error on a cosmic scale, mirroring the very processes that shaped life itself. Experimentation remains one of the most definitive tools for advancing science, yet even this takes a secondary role to problem solving. The most elegant and robust theories often make bold predictions, laying out scenarios that can be meticulously tested. A single wrong prediction may falsify an entire theory, but a correct prediction, while valuable, does not definitively prove its validity. Instead, these experiments act as stepping stones, fueling the ongoing search for explanations that provide greater depth and clarity. At the heart of scientific progress lies the search for better explanations. A good explanation is not just one that fits the observable data, but one that is broad, deep, and resilient against criticism. Theories that fail to provide strong explanations, no matter how accurate their predictions, remain inferior. Science, therefore, advances not simply by adding to what we know, but by replacing weak ideas with ones that offer profound insight into the mysteries of the universe. The search for knowledge isn't static. There's no final endpoint, no ultimate truth waiting to be discovered. Each breakthrough brings its own set of new questions, driving further exploration. Today's best theory is tomorrow's stepping stone, as we continue pushing the boundaries of our understanding. This unending refinement of explanations is what makes science not a quest for answers, but a continuous, evolving pursuit of better knowledge. Space challenges us to think beyond what we know, reflecting science as a system of possibilities, not finalities. Each discovery deepens our understanding of existence and connects us to the universe. As we explore the cosmos, we expand the horizon of human potential. Imagine looking up at the night sky. The vast emptiness you see is just one piece of an incredible puzzle we've been trying to solve for centuries. But here's the thing: how do we know what we know? How can we be sure what's out there is real and not just a figment of imagination? First, let's start with explanations. Explanations in science aren't about justifying things through their origins or proving them in an absolute sense. Instead, they're evaluated based on how well they solve problems and help us understand the world. For an explanation to stand its ground, it must justify itself. Essentially, it needs to hold up under scrutiny. It's not enough to provide an answer if that answer can't be defended logically or scientifically. The search for definitive ultimate justification, that's a dead end because no such source exists. Everything we know comes from questioning, testing, and refining ideas. And that's the beauty of science. It's an ongoing story, not a finite book. Now, what about solipsism? This philosophical notion claims that only one mind truly exists, and everything else, other people, the universe, reality itself, is just a dream within that mind. But the issue with solipsism is that it collapses under its own weight. Take it seriously and it unravels. Why? Because our daily lives, scientific achievements, and even these very thoughts you're hearing all rely on the assumption that reality exists independently of us. Imagine trying to land a spacecraft on a distant planet, while sincerely believing the universe is just a projection of your imagination. Doesn't work, does it? Scientific reasoning inherently dismisses solipsism because it assumes a shared reality that we can investigate through observation and experimentation. Speaking of observation, here's where things get trickier. If repeated observations form patterns, why can't those patterns permanently prove a theory? This brings us to the problem of induction. Just because something has happened repeatedly in the past doesn't guarantee it will happen the same way in the future. Think of an apple falling from a tree. It's fallen down every time so far, but can we prove it will always do so? The philosopher Karl Popper offered a solution. Rather than building scientific knowledge through induction, he argued science progresses through bold conjectures and relentless refutations. Theories are tested to their limits and replaced or refined when they fail. Science isn't about proving something beyond doubt, but about surviving criticism better than alternative explanations. And then, there's the question of reality itself. You may believe we can all agree on what's real, but defining reality isn't as straightforward as it seems. Reality in scientific terms is not an absolute concept. Instead, it's a judgment based on our best available explanations. Consider this: gravity was once seen as a mystical force pulling objects downward. Then Einstein reframed gravity as the curvature of space-time. Both explanations aim to describe the same phenomenon, but Einstein's description was a step closer to understanding it more accurately. What's real evolves as our theories improve. Sometimes reality kicks back at us literally. Dr. Samuel Johnson once famously dismissed philosophical disputes about the existence of reality by kicking a stone and declaring, "I refute it thus." His point was simple: if something acts upon us, if it makes itself felt in our experience, it's likely real. Galileo used this same principle when his telescope revealed the existence of planets. The light entering his telescope interacted with his eyes, offering tangible evidence that the planets were more than just dots of light. They were real celestial bodies. Science applies this principle time and again to distinguish between what's real and what's an illusion. But here's something truly humbling about science. Our explanations don't just help us uncover reality. They also change what we consider to be real. Think of Newton's concept of gravity, once the ultimate truth, which later gave way to Einstein's more complex explanation of space-time curvature. It's like peeling back layers of an onion. Each layer reveals more, but the core keeps moving as we expand our understanding. This evolution is tightly linked to complexity and autonomy, two markers of reality. Real entities tend to exhibit complexity and act autonomously. Think about a planet versus a reflection in a mirror. A planet has its own complexity. It exists independently of you, or the way you choose to observe it. A reflection, on the other hand, borrows its complexity from the object it reflects. The more autonomous and complex something is, the more likely it is to be real. Now, some might argue, but isn't science just about observing and generalizing? Isn't that all inductivism is? That's a misconception. Science thrives not on mere repetition, but on building explanatory frameworks. Theories are tested, refined, and chosen, not because they're proven, but because they withstand criticism better than the competition. For instance, Einstein's theory of relativity wasn't accepted because someone observed it 1,000,000 times. It was accepted because it provided a better explanation for reality than Newton's laws in certain circumstances. Here's the most exciting part: science is never final. The criteria for what's real are open-ended and constantly improving. Each breakthrough creates new questions. Just as the concept of gravity evolved from Newton to Einstein, so too will our current theories transform as new discoveries emerge. The universe is far too vast and complex for us to stop exploring, questioning, and refining. Ultimately, this open-ended nature is what makes scientific inquiry so exhilarating. Every explanation is a stepping stone to better understanding, and every discovery hints at new layers still waiting to be uncovered. It's not just about answering questions. It's about asking better ones, the kind that lead us into uncharted territory. Have you ever looked up at the night sky and wondered, what's really out there? How do we know that all those twinkling lights aren't just illusions created by our own senses? It's one thing to observe space through a telescope, but how do we confirm that what we're seeing is actually real and not just some grand trick of the mind? Today, we're going to tackle a fascinating question about our relationship with reality, perception, and the cosmos. It's called the space problem, and believe me, it's not just about the vast, endless void above us. It's also about how we determine what's truly real. To understand this, we need to introduce a simple yet profound concept referred to as the test of kicking back. At its core, this principle asks a crucial question. Does what we observe kick back at us? That is, does it interact with us in ways that require an independent explanation? If it does, then we can consider it to be real. If not, it may remain confined to the realm of illusions or mental constructs, leaving its actual existence in doubt. Hold on to this idea, because it's the key to unraveling the space problem. Now, this idea of kicking back sounds almost playful, doesn't it? Like tossing a ball against a wall and watching it bounce back toward you. But don't underestimate its significance. It's an incredibly practical tool to separate reality from mere perception. You see, our senses can be deceived. Think about it. For centuries, people believed in mirages, hallucinations, and other sensory tricks. Reality needed a higher standard of proof. And that's where this idea of interaction, this kickback, comes into play. To bring this concept to life, let's travel back to one of the most pivotal moments in human history. The year is 1609. Galileo Galilei, a man of boundless curiosity and intellect, turns his newly improved telescope skyward, aiming it at Jupiter. What he sees astonishes him. Tiny luminous dots, moons, are orbiting the gas giant, a discovery that challenges the very foundation of the universe as it was understood at the time. But here's the twist. Skeptics argued that these moons, as extraordinary as they seemed, were nothing more than illusions. They believed these celestial objects were figments conjured up by imperfections in Galileo's telescope, artifacts of his lens, rather than real celestial bodies. However, Galileo had a counter-argument. He observed that the light from these moons physically interacted with his eyes. The way it changed, shifted, and moved could not be fully explained by simply blaming imperfections in the lens. The light had properties that interacted with him in ways requiring explanation beyond his telescope. The moons kicked back, so to speak, and in doing so, they proved to be real entities, not optical illusions. This same principle of interaction, of kicking back, has shaped the very foundation of science. Take the example of electrons. These tiny particles are invisible to the naked eye, yet their effects can be seen in cloud chambers, where they leave tracks as they collide with molecules of gas. These tracks, their kickback, are the undeniable proof of their existence. Without it, electrons might remain mysterious whispers in equations. But thanks to their visible interaction, we know they're not merely theoretical constructs, they're unquestionably real. Now this brings us right back to the space problem. Some philosophical schools of thought suggest that everything we observe might simply be a mental construct, a projection of the mind. If reality exists only in our perceptions, if the stars, planets, and galaxies are only fragments of an elaborate internal tapestry, how can we trust what we see? Here's where that test of kicking back becomes so powerful. The moment an entity produces observable effects that go beyond our own sensory experience, they prove their independence from us. Think about the cosmic rays that bombard Earth from far-off galaxies. They are invisible to our eyes, yet they interact with detectors, unleashing measurable effects that demand explanation. These rays didn't come from us, nor do they rely on our perception to exist. They exist in their own right, proving their reality in the way they kick back against the world around them. This principle might appear straightforward, but it has massive implications. It means that our reality isn't limited by our personal perceptions. It's not confined to what we sense or believe. Reality pushes back. It interacts. It forces us to confront its existence. And it's this pushback that grounds us in the truth. The space problem, then, isn't just about the great void of the cosmos. It's a question of epistemology, a fancy way of asking, how do we know what we know? It challenges us to examine how we differentiate between what's real and what's imagined. It invites us to explore the ways the universe kicks back, making us realize that every push, every interaction is a conversation between us and the cosmos. Galileo's telescope, the tracks of electrons, the cosmic rays, they all tell a similar story. They remind us that reality is defined not just by what we observe, but by how those observations interact with us. The planets kick back through the telescope. The electrons kick back in cloud chambers. The universe kicks back through particles and waves we can't see but can measure. Our understanding of reality is a story that keeps unfolding. What we once believed to be fixed truths about the universe often change as we uncover new layers of understanding. Think about it. What does it even mean to comprehend reality? Is it something permanent, or does it evolve as our explanations deepen and improve? For astronomy enthusiasts and space lovers alike, grappling with this idea is part of the thrill, isn't it? The very fabric of what we accept as true is constantly rewritten with each passing discovery. Look back at history. Imagine living in the era when Isaac Newton's theory of gravity captivated the world. For centuries, Newton's vision gravity as an invisible force acting at a distance was fundamental. It transformed the way humanity saw the universe, offering clarity and structure to celestial observations. Yet, fast forward to the 20th century, when along came Albert Einstein with his groundbreaking general relativity. Suddenly, gravity was reimagined. It wasn't just a force anymore. It was the curvature of space-time itself. Picture space as a stretched sheet with planets and stars creating dents, pulling objects toward them. Einstein didn't invalidate Newton's concept, but presented a deeper, more refined explanation. The shift reminds us of something critical: reality isn't fixed. It evolves as our understanding does. Consider atoms. For ages, they were thought of as the ultimate indivisible building blocks of matter. The word itself stems from the Greek atomos, meaning unable to be cut. But as science progressed, we uncovered intricate layers within these so-called indivisible particles. Electrons, protons, neutrons, an entire internal universe revealed itself. And then came quantum mechanics, which took understanding to an even stranger, almost surreal level. Imagine particles behaving like waves, interfering with themselves, all while defying our classical understanding of things occupying space. These discoveries transformed our sense of what matter really is. It doesn't stop there. Imagine listening to early geologists rejecting the notion of continents drifting across Earth's surface. When Alfred Wegener first proposed continental drift, the majority scoffed. The idea of massive landmasses moving over time seemed absurd, unrooted in any solid evidence. Yet today, plate tectonics, founded on decades of additional research, is a bedrock principle in geology. The land beneath our feet, something seemingly permanent and immovable, is actually dynamic, shifting relentlessly, albeit slowly. A reality we take for granted now was once seen as utterly implausible. Or what about the microscopic world of fundamental particles? Quantum particles like electrons were initially thought of as strange mathematical abstractions, an attempt by physicists to explain experimental results that challenged conventional theories. But as experiments evolved, like observing electron interference in double-slit experiments, these imaginary quantum entities became undeniably real. The proof overwhelmed skepticism, anchoring the once abstract ideas firmly in the domain of reality. The lesson here is profound. Science doesn't just stack knowledge on top of existing realities. It reshapes what we recognize as real. The history of scientific discovery is filled with shifts in perception like these. Gravitational waves, for instance, were once theoretical ripples in space-time, predicted but unconfirmed. That is until observatories like LIGO and Virgo detected them, confirming Einstein's predictions from nearly a century ago. Black holes? A concept born in equations that spiraled out of early 20th century physics, finally confirmed with direct imaging in 2019. Dark matter and dark energy? These enigmas currently hang in the balance, still hypothetical, yet holding the potential to redefine reality all over again as our instruments and theories improve. And what about us? You and I? The act of comprehending these scientific revolutions forces us to reconsider our place in the universe. It's dizzying, yet exhilarating, isn't it? Reality, it appears, isn't this static, fixed construct. It expands, reshapes, and even overturns itself with every new explanation. This brings us to the inevitable question, what's next? What aspects of the universe might we currently dismiss as unreal, imaginary, or impossible that future generations might accept as fundamental truths? Could it be extraterrestrial life? Multiverses? Entire dimensions of existence we've yet to capture even a glimpse of? The possibilities, much like the cosmos itself, are endless. The evolution of scientific thought teaches us humility. It tells us to hold on to our current understanding with curiosity, but not rigidity. For what we know today might merely be a stepping stone toward deeper truths. Every time we innovate, every time we ask better questions, we move closer to understanding the cosmos and our place within it. What mysteries could redefine our realities tomorrow? The universe has much left to reveal. Inductivism, the idea that knowledge arises from repeated observations, has long been a staple in many traditional views on science. It seems logical on the surface: observe something happen enough times, and you'll arrive at a universal truth, right? But this way of thinking is flawed at its core, and here's why. Imagine we observe that every day the sun rises in the east. Inductivism would tell us that since it has always risen in the east, it will continue to do so indefinitely. But this doesn't explain why the sun rises, or give us any understanding of the mechanisms behind it. Simply stacking observations atop one another offers no guarantee of truth. Science at its heart demands explanations, not just predictions. Karl Popper, a revolutionary thinker in the philosophy of science, saw through the shortcomings of inductivism. He suggested that science does not progress by confirming theories through repeated observations. Instead, it advances through conjectures and refutations. This means we progress by proposing bold theories, conjectures, and then rigorously attempting to falsify them. A theory doesn't grow stronger from the number of times it has been confirmed. It becomes more robust when it survives challenges and criticism. Think of theories as ideas being forged in the fire of scrutiny. The heat either strengthens them or melts them down entirely, making way for better, more refined ideas to emerge. This leads us to the role of explanation in science, which Popper emphasized. Theories should not just aim to predict what will happen, but they must offer deep, meaningful explanations. For example, Newton's laws didn't just predict the motion of planets. They illuminated the underlying forces governing those motions. They solved problems. Great scientific theories weave themselves into the tapestry of existing knowledge, not just by accounting for observations, but by expanding our understanding. Theories that merely attempt to echo past events without explaining them are inadequate. They are like band-aids, offering a temporary fix rather than healing the root of the issue. Now, herein lies one of the most revolutionary ideas within this discussion. Science does not have an ultimate foundation. The search for an unshakable, absolute justification for all scientific knowledge is a wild goose chase. There is no single bedrock of truth from which all knowledge springs. Instead, knowledge evolves through the continuous process of criticism and refinement. This may sound unsettling at first. After all, aren't we wired to search for certainty? But think about it. This very process of improvement is what keeps science alive. Like climbing an endless staircase, there isn't one final step that leads to absolute truth. Instead, each step takes us higher, revealing a clearer but still incomplete view of reality. Rationality itself isn't justified by some ultimate proof. It's its ability to evolve, adapt, and improve explanations that validates it. This debate, the tension between inductivism and explanation-driven science, is vividly illustrated in a conversation where one side argues that science's justification doesn't come from an external principle sitting outside the domain of explanation, but from its very ability to solve problems and make sense of the world. The opposing view clings to the need for some missing link, a foundation to justify all scientific theories. However, the counterpoint is compelling. Science doesn't need an ultimate justification because its power lies in its problem-solving quality, not in proving itself beyond reproach. Theories that solve more problems better and deeper are inherently superior to those that don't. One of the fascinating pillars of this discussion is the Turing principle. This principle proposes that a universal virtual reality generator could, in theory, simulate any environment physically possible. What does this mean for knowledge creation? It underscores the idea that the universe is inherently knowable and that human beings, through their capacity for creativity and explanation, are part of this remarkable mechanism. The ability of the human mind to create knowledge isn't just a lucky accident. It's an intrinsic feature of our existence. The universe itself supports the creation of knowledge, and through its laws and principles, it allows us to explore and explain its mysteries. When it comes to the question of when we can declare a theory true, science doesn't indulge in certainties. The process of corroboration. When a theory survives numerous attempts to falsify it, grants it resilience but doesn't equate it with truth. No theory, no matter how well tested, is immune to potential revision. This humility is what allows science to progress. Newton's laws, once viewed as sacrosanct, were refined by Einstein's theories. Theories remain tentative, open to criticism and evolution, ensuring we stay flexible in pursuit of deeper understanding. This leads us to the practical application of all this philosophy. How do we act rationally in the face of uncertainty? Decisions, whether in science or daily life, rest on the best available explanations, not on absolute certainties. Science's greatest strength lies in its utility. It works. It solves problems, provides frameworks for innovation, and gives us tools to shape our world. The demand for an unshakable foundation is not only unrealistic but also unnecessary. The effectiveness of science in improving lives, driving technology, and expanding human understanding demonstrates its value. It moves forward not through dogma but through the relentless pursuit of better explanations. And so, we find ourselves at the heart of what makes science such a powerful tool for humanity. It thrives, not on certainties, but on its ability to adapt. It doesn't seek ultimate truths locked away in some unreachable vault. Instead, it seeks to solve problems, sometimes small, sometimes monumental. It gives us a framework to explore the universe, to understand our place within it, and to harness the laws of nature in extraordinary ways. For those of us gazing at the stars and pondering the fabric of reality, isn't this constant striving for better explanations what makes science so profoundly exciting? Instead, it seeks to solve problems, sometimes small, sometimes monumental. It gives us a framework to explore the universe, to understand our place within it, and to harness the laws of nature in extraordinary ways. For those of us gazing at the stars and pondering the fabric of reality, isn't this constant striving for better explanations what makes science so profoundly exciting? Ancient thinkers perceived living beings as fundamentally distinct from the inanimate world. Aristotle, for example, believed life could be defined by its ability to initiate motion, a spark of activity that set it apart from non-living matter. But as modern science evolved, this view was dismantled, replaced by a reductionist perspective. Today, life is often seen as a chemical process, governed entirely by the same physical laws that direct the movement of stars and the erosion of mountains. Yet, even with this explanation, life remains an undeniable enigma, a central force wrapped in the fabric of reality. Life is not just a result of physics. It is a phenomenon that gives the universe a unique dynamism. Unlike inert matter, life acts with purpose and adapts with knowledge. Across the vastness of existence, life stands out for its ability to affect its surroundings in deliberate, meaningful ways. It is not surprising, then, that understanding life is key to understanding the universe itself. We cannot fully grasp cosmic events without acknowledging how life interacts with them. At its core, life is the embodiment and creator of knowledge, a force continuously learning, adapting, and reshaping. When we look inside the living cell, we find a staggering level of organization. Within DNA lies the story of life, an incredibly intricate code, storing knowledge about survival, reproduction, and adaptation. This molecular program, written over billions of years of evolution, acts as a blueprint for living organisms. Through trial and error, life has come to master the art of existing in an often hostile universe. Yet DNA is not alone in its role. Every living thing, no matter how simple or complex, holds and propagates this intrinsic arsenal of knowledge. When we scale up from the cellular to the cosmic level, life's impact becomes even more extraordinary. Over long periods, life doesn't just adapt to the universe. It has the potential to reshape it. Cosmologists speculate that intelligent life may one day influence galaxies and entire universes. Imagine stars being harnessed as energy sources or planetary systems being designed by advanced beings. These are not just fanciful science fiction notions. They are plausible projections based on life's trajectory when combined with technological progress. Life holds within it the potential to alter the ultimate fate of the cosmos. This brings us to a fascinating idea, the multiverse perspective. If multiple realities exist, as some physicists believe, life might leave its mark on a scale far greater than we can imagine. Knowledge-bearing systems, such as DNA in biology or neural systems in intelligent beings, display an order and design that could echo across parallel universes. Genes replicate across generations, preserving essential survival information, while memes, the intangible ideas and cultural practices we share, propagate through human societies and leave lasting imprints. These replicators ensure that the influence of life transcends the boundaries of any single world or dimension. Life also reflects a computational brilliance. The Turing principle, long a foundational concept in computer science, reveals an intriguing parallel between life and computation. It suggests that all physical laws can be encoded in a program, much like the way DNA encodes biological information. This computational nature means life realizes principles of biology, physics, and computation in elegant harmony. Each living organism, from the simplest bacterium to the most complex human being, is essentially a biological algorithm running on the operating system of the universe. But life's importance doesn't end with knowledge acquisition or computational prowess. Its influence extends to the fundamental processes of cosmic evolution. Human beings, for instance, possess not just the ability to survive, but also to shape the future. The decisions we make, the technology we invent, and the knowledge we gather collectively determine the trajectory not just of life on Earth, but perhaps life throughout the universe. If intelligent life endures long enough, it may control planetary systems, stars, and even astrophysical processes that today seem devoid of intervention. What happens to stars, galaxies, and interstellar matter could eventually depend more on the will of intelligent systems than on natural phenomena like gravity or entropy. On one hand, life might seem insignificant when compared to the sheer mass and energy of the cosmos. The collective weight of all living organisms is minuscule compared to a single sun, yet its influence is uniquely profound. While non-living matter drifts passively through time, life is perpetually reshaping its environment, whether it's building civilizations, altering ecosystems, or crafting technologies that reach beyond the confines of the planet. Unlike inanimate objects, life develops strategies, solves problems, and navigates the cosmos driven by an insatiable desire to understand and adapt. When we consider this, life becomes the dominant force of influence in the universe, despite its small physical presence. It's not mass or energy that defines life's importance, but its capacity to generate change and steer its surroundings. The very fate of the universe, across millennia or eons, may be shaped less by inevitable physical laws and more by the persistent and purposeful progression of life. Life, then, is more than just chemistry in action. It is the fabric upon which the future of everything may depend. A biologically driven force that accumulates knowledge, teaches itself to harness energy, and someday may even rewrite the story of the cosmos itself. Mathematics is often thought of as a pure abstraction, a set of concepts that exist in a realm far removed from our physical reality. But what if mathematics isn't just an abstract discipline, but rather a key to understanding the fabric of reality itself? Instead of seeing equations and numbers as mere mental constructs, they can be viewed as part of the intricate structure of the universe, deeply intertwined with the physical world we inhabit. This notion challenges the belief that mathematics solely resides in human imagination, prompting us to reconsider its relationship with everything we think of as real. Take numbers, for instance. They aren't tangible objects we can hold or see, yet they underpin the way we understand patterns, measurements, and relationships. From counting stars in the night sky to calculating vast interstellar distances, numbers guide how we make sense of reality. While they don't exist in the same way a tree or a rock does, they undeniably play a role in the foundational functions of our universe. This opens up a fascinating question. Where do such abstract entities exist, if not in physical reality? If they are independent of human thought and yet play a role in describing the universe, their nature blurs the line between abstraction and reality. Mathematics is not just about crunching numbers or solving equations. It's also about offering explanations. Contrary to the idea that mathematics provides absolute truths, our understanding of these truths is as subject to change as any scientific theory. Proofs, often considered the bedrock of mathematics, rely on physical processes. These include writing on paper, processing information through computers, or even the workings of the human brain. Math isn't a collection of eternal certainties. It's a living, breathing process of discovery and understanding, shaped by the tools and minds that explore it. Kurt Gödel's groundbreaking incompleteness theorem adds another layer to this understanding. He showed that no mathematical system, no matter how sophisticated, could be entirely complete or self-contained. Within any sufficiently complex system, there will always be truths that cannot be proven from within. This revelation demonstrates that mathematics, like science, requires creativity. It isn't a simple exercise in following rules. It demands the invention of new ways of thinking and proving. Gödel's work highlights that mathematics is anything but a closed system. It's vibrant, open-ended, and full of surprises. Consider this in the context of mathematical certainty. Historically, many have viewed mathematics as an unshakable structure on which we base knowledge, but even basic axioms have been questioned and revised. Take Euclid's parallel postulate in geometry. It once seemed self-evident, yet revisions to it gave rise to non-Euclidean geometry, which turned out to be crucial in understanding Einstein's theory of relativity. Relativity itself demonstrates how even the most fundamental mathematical constructs are tested and revised through empirical observation. Mathematics, then, is not a fortress of absolute certainty, but rather a tool that evolves with our understanding of the universe. At its heart, mathematics serves as a window into reality rather than a rigid framework. Proofs aren't validated solely by formal logic. They must resonate with our understanding of the world. Hilbert's program aimed to establish an unshakable foundation for mathematics, but was ultimately undone by Gödel's discoveries. What we're left with is not a failure, but a new appreciation for mathematics as a process of explanation, one deeply connected to how we perceive and interact with the universe. The relationship between mathematics and physics further deepens this connection. Far from existing as an independent system, mathematics is inextricably tied to the physical world. The reliability of mathematical truths is contingent upon the same physical laws that govern our universe. Mathematical models depend on physical objects, computers, instruments, or even neurons in our brain for their creation and validation. This symbiosis reveals that mathematics is not an isolated entity, but one thoroughly embedded in the framework of reality. And yet the illusion of mathematical certainty persists. This idea that math offers absolute truths still lingers, but if history tells us anything, It's that nothing remains unquestioned. Geometry, arithmetic, set theory, all have seen foundational shifts that reshape how we conceptualize them. This fluidity doesn't diminish the power of mathematics, but underscores its dynamic role in exploring and explaining the cosmos. The beauty of mathematics lies not in its supposed infallibility, but in its capacity to adapt, evolve, and reveal the intricacies of the universe. To view mathematics solely as a set of answers to predefined problems is to miss its broader significance. Instead, it is a way for us to understand and interpret reality. It's a language that describes phenomena both seen and unseen, a framework through which we can probe the mysteries of existence. The traditional Platonic belief that mathematical entities exist in a separate, perfect realm is challenged by the perspective that these elements are deeply rooted in computation, physics, and our cognitive processes. Ultimately, mathematics is a human endeavor, shaped by our imagination, our creativity, and our tools. It bridges the abstract with the tangible, transforming ideas into explanations that bring us closer to the heart of reality itself. While it may never offer absolute certainty, its true power lies in its ability to guide us in our ongoing quest to understand the universe. Time, a concept that feels so familiar, yet unravels into mystery the moment we attempt to define it. It isn't something we can touch, but it's deeply woven into the fabric of our reality. We experience life through a sequence of moments, yesterday, today, tomorrow, so smoothly that it feels as though time itself is flowing. But what if this flow of time is not real? What if everything we believe about time is merely an illusion? This question lies at the heart of one of the most fascinating riddles in physics. The peculiar nature of time has puzzled thinkers for centuries. St. Augustine once remarked, "If no one asks me what time is, I know, but if I wish to explain it, I do not." It's intriguing how something so integral to our existence can evade definition. Unlike space, which is static and unmoving, time seems to have a unique quality: its apparent movement from past to future. Yet, physics offers a radically different view. The common intuition is that time flows like a river, carrying us relentlessly forward. We mark our lives by its passing, from a child's first steps to the whispers of old age. This common-sense perception suggests the present moment is constantly moving, progressing 1 second at a time. But here's the catch: physics doesn't agree. Time, according to science, is not a flowing entity. Instead, it's a dimension, similar to space. Albert Einstein's theory of relativity cemented this idea, showing that time intertwines with space to form a vast, four-dimensional structure called space-time. Newton, one of the greatest minds in physics, described time as absolute, true, and mathematical, ticking on uniformly like the steady beat of a drum. Yet even he treated time as static, something that didn't really move, but existed as a background against which events played out. The perception of time flowing, therefore, is not built into the laws of physics, but rather into human intuition. It feels real, but so does the sensation of standing still on a spinning Earth. If time doesn't flow, then what is its true nature? Here's where quantum mechanics brings even more intrigue. Unlike classical physics, which views time as continuous and universal, quantum mechanics suggests a fragmented universe, one made up of interconnected snapshots rather than a seamless stream. Quantum physics forces us to confront a bizarre idea that these moments don't necessarily stick together in a nice linear fashion. Imagine a photo album where each picture exists independently. Quantum theory suggests this might be closer to reality than the comforting narrative of events flowing forward in an unbroken sequence. This raises a peculiar question. If moments are just snapshots, what determines their order? Classical physics tells us that every moment is a result of the ones before it, like a carefully lined domino set where one falls and leads to the next. But quantum mechanics paints a new picture, one where events aren't tied to a strict sequence, but are instead connected probabilistically. This viewpoint is pivotal to how we understand causality, the idea that one event causes another. Consider a simple coin toss. Classically, once the coin lands, it will show either heads or tails. But in the quantum realm, before observation, the coin exists in a superposition. It's both heads and tails simultaneously. Only when you observe it does the coin choose an outcome. Yet this is where it gets even stranger. The act of observation doesn't just decide the present, it influences the past as well. Suddenly, the concept of linear cause and effect starts to break down, leaving us with a puzzling, interconnected web of possibilities. When we look at extreme environments like near the Big Bang or inside black holes, the concept of classical time falters completely. At the moment of the Big Bang, when the universe burst into existence, time as we understand it might not have existed. Quantum effects prevented time from having a clear order, suggesting time itself could have emerged from something more fundamental. Similarly, near black holes, where gravity stretches and warps space-time to its limits, the classical concept of time gives way to something entirely counterintuitive. This brings us to two competing ideas about time and existence: the block universe and the multiverse. The block universe, rooted in classical physics, portrays space-time as a vast, unchanging structure where past, present, and future coexist simultaneously. Imagine a loaf of bread, where each slice represents a moment in time. All the slices are there, they don't disappear or move. However, the quantum multiverse presents an entirely different narrative. Instead of a single loaf, we have countless loaves, each representing a different version of reality. Within this framework, what we call the past is just one configuration among many. Our reality becomes one of countless possibilities, shimmering across the vast expanse of the multiverse. This perspective changes how we think about free will. If time doesn't flow and the future already exists in the multiverse, do we truly have a choice in what happens next? From the multiverse's point of view, every possibility already plays out somewhere. Yet for us as individual observers, the future feels like it's ours to shape. Free will then might not be a fundamental property of the universe, but rather an emergent experience, a byproduct of our perception of time's passage. And here's where the possibility of time travel enters the picture. If time is just another facet of the multiverse, it might be possible to move through it, just as we move through space. Some theories even suggest the existence of closed, time-like curves loops in space-time, where events in the future influence their own past. While this remains speculative, the very idea challenges conventional notions of cause and effect. Practical time travel, however, remains an open question, wrapped in layers of scientific and philosophical debates. What does all of this mean for our understanding of time? It challenges us to reconsider the distinction between past, present, and future as artifacts of human perception, rather than features of reality itself. Time doesn't flow, but exists as a structure within the multiverse, a framework that, while counterintuitive, aligns with the most advanced theories in physics. By exploring time through the lens of quantum mechanics, we gain a profound glimpse into the interconnected and mysterious nature of the universe. Time may evade our grasp, slipping through our fingers like a phantom. But by peeling back its layers, we begin to uncover a landscape far more intricate and awe-inspiring than we could have imagined. A landscape not of fleeting moments, but of infinite possibilities, waiting to be explored. Time travel, just saying the phrase, sparks endless fascination and curiosity. It conjures images of zipping through history or jumping forward to glimpse the unknown future. But what does time travel actually mean? Is it the stuff of science fiction, or does it have roots in scientific theory? The conversation about time travel is more complex, intriguing, and mind-bending than we might think. It opens doors not just to stories of possibility, but to deep questions about the reality of the universe itself. At its core, time travel is about moving between different moments in time, much like we traverse distances in space. Once we consider time as a fourth dimension, alongside length, width, and height, the concept of moving through it becomes more tangible. Instead of being a one-way river flowing from past to future, time can be seen as snapshots of existence, all existing simultaneously in a framework that allows for exploration. But here's where it gets fascinating and, admittedly, tricky to comprehend. Unlike science fiction movies that show time machines as vehicles punching through timelines, the scientific perspective suggests something more intricate. The idea isn't traveling through time as we drive down a highway. Instead, it's about altering the relationship between these snapshots of existence. When we speak of future-directed time travel, we're stepping into one of the least controversial aspects of the topic. This type of time travel actually happens, validated by Einstein's theories of relativity. Picture astronauts traveling near the speed of light. For them, time on their spacecraft moves slower than it does for people on Earth. They return to a world where more time has passed than they've experienced. In essence, they've leaped into the future. Similarly, slowing biological processes, such as through forms of suspended animation, creates another method of experiencing future-directed time travel. From science fiction to real-world experimentation, this approach feels almost within reach because it doesn't violate our understanding of causality. Past-directed time travel, however, is where things start to twist into philosophical and scientific knots. The idea raises a plethora of concerns, particularly about paradoxes. If you could venture into the past, how would the actions you take there unfold? Imagine you interfered in your ancestors' lives, preventing your own birth. This classic example, known as the grandfather paradox, questions whether consistency is maintained in time, or if such interferences could dismantle logical causality. Additionally, other paradoxes, such as the knowledge paradox, add fascinating complexity. For instance, if someone brought a future manuscript of Hamlet back to Shakespeare, how can we pinpoint its true creation? These scenarios unearth profound issues about the coherence of time travel. Scientific exploration suggests that time machines, as imagined by physicists, aren't vehicles in the traditional sense, but rather places or pathways. Einstein's equations propose that closed time-like curves, essentially loops in space-time, could theoretically form around objects like spinning black holes or with exotic matter. These conditions are not only extreme but incredibly speculative. Yet, what's remarkable is that no currently known laws of physics outright prohibit past-directed time travel. But achieving it would require technological capabilities far beyond what we have today, pushing the boundaries of possibility into uncharted territory. Paradoxes aren't just entertaining thought experiments. They hint at deeper truths about the nature of our reality. Think about the grandfather paradox or the knowledge paradox. They force us to question whether traveling into the past disrupts causality or, as some theories suggest, diverts us into alternate timelines. One explanation relies on the multiverse theory, an idea as breathtaking as it is unsettling. Traveling to the past may mean entering a parallel universe rather than altering events in our own history. If we think about it, this perspective doesn't close the door on time travel, but instead reframes its implications entirely. But how do we explore a concept as perplexing as time travel? Virtual reality offers compelling tools to simulate these ideas. Simulating a consistent and interactive version of the past in VR, however, reveals another layer of complexity. The nature of virtual reality attempts to immerse us in different environments and experiences, yet it struggles when applied to phenomena governed by paradoxes. The Turing principle suggests that a universal virtual reality generator should be capable of simulating any physically possible environment, even scenarios involving time travel. It's a remarkable idea that further blurs the line between feasible exploration and imaginative speculation. Time travel also intersects with computation in ways that are as exciting as they are mind-boggling. A functional time machine, in theory, could create unprecedented possibilities for computational problem-solving. Imagine being able to access information from the future to resolve issues in the present without the need for traditional computation. It would revolutionize problem-solving, granting results drastically faster by leveraging information from across multiple universes. The efficiency of such a system could reimagine how we approach complexity and uncertainty. While the conversation around time travel continues to fascinate science enthusiasts and thinkers alike, it's important to recognize its theoretical limits. Future-directed time travel, as we've discussed, aligns with modern physics and feels closer to technological realization. Past-directed time travel, on the other hand, teeters on the speculative edge. Physicist Stephen Hawking even proposed a chronology protection conjecture, surmising that quantum fluctuations may prevent time loops from forming naturally. Even if such time travel were possible, the implications would be profound and possibly limited. Visitors from the future wouldn't inform us about our timeline, but would stem from parallel universes instead. The implications of time travel stretch beyond our fascination with bending the fabric of reality. It challenges our understanding of causality, the flow of information, and the structure of the multiverse. If time travel is one day realized, it wouldn't just redefine what's feasible in science. It would fundamentally shift how we perceive existence. Experiments that venture into the unknowns of causality and knowledge could yield groundbreaking insights into quantum mechanics, computation, and philosophy. Time travel remains as much a frontier of imagination as it is of scientific inquiry, connecting realms of discovery in ways that continue to inspire wonder. The quest to understand the very fabric of reality is unlike any other endeavor in human history. It's not just about physics, philosophy, computation, or biology. It's about how all these elements come together in an intricate, interconnected tapestry. To truly grasp the universe, we need a unified framework that stretches across disciplines and integrates knowledge into one coherent explanation. It is through this lens we can explore the multiple strands of reality and their significance. The foundation of this exploration begins with the realization that knowledge cannot exist in silos. The fabric of reality isn't confined to the physical laws of the universe. It encompasses deeper principles that govern thought, computation, and evolution. This holistic perspective calls for moving beyond isolated frameworks and toward an integrated understanding, one that acknowledges that no single field alone can provide the answers we seek. This drive for unification, to combine knowledge from multiple disciplines, forms the bedrock of our exploration into the vast unknown. At the heart of this fabric are the four fundamental strands of reality. The first is quantum physics, the pillar of our understanding of the physical universe. It explains the underlying mechanisms that govern matter, energy, and the cosmos. Quantum theory, including the many worlds interpretation, reveals a universe far more complex and expansive than traditional physical models suggest. It teaches us that reality isn't singular. It's a symphony of intertwined possibilities. But physics alone cannot answer deeper questions about the nature of knowledge and its growth. This is where epistemology becomes critical, a second strand that explains how scientific theories develop and evolve. Knowledge is not static. It grows through a process of conjecture and falsification. Every theory stands as a foundation, open to refinement or even replacement by better, more explanatory successors. Without epistemology, we'd lack the tools to understand why knowledge progresses, why it sometimes stalls, and how it can leap ahead. The third thread that weaves into this fabric is the theory of computation. Computation goes beyond simply processing numbers. It captures how information is manipulated, understood, and applied. Consider how algorithms power the devices we rely on daily. These same principles of computation shape the very fabric of the universe, providing the blueprint for how reality itself processes information. It's a mesmerizing realization that computation is not just a tool for humans, but a fundamental aspect of the universe. Completing the quartet is the theory of evolution. Evolution provides a framework for understanding complexity, whether in biological systems or non-biological ones. It explains adaptation, the emergence of novelty, and the development of intricate systems capable of remarkable feats. From the diversity of life to the design of cutting-edge AI, evolution is a testament to how simple rules can yield unimaginable complexity over time. While each strand, quantum physics, epistemology, computation, and evolution, addresses a vital aspect of reality, they cannot be viewed in isolation. Separately, they may seem cold, narrow, and mechanical, leaving gaps in our understanding. It is only when they are interwoven into a unified explanatory framework that they transcend their individual limits and reveal the broader fabric of reality. Reductionist approaches that break down phenomena by relying solely on physics cannot provide the complete picture. The strands must collaborate, each amplifying the other's strengths, to illuminate truths that were once hidden in disciplinary shadows. Yet even with this integration, we must acknowledge a significant challenge: explanatory gaps. Across different scientific fields, gaps persist where existing theories fall short. For instance, while quantum physics and computation illuminate vast aspects of the universe, the relationship between the two, how information emerges from physical laws, remains elusive. Similarly, evolution and epistemology raise profound questions about why knowledge grows, why complexity emerges, and why these patterns persist across entirely different systems, from DNA to human culture. Quantum mechanics, too, presents mysteries that challenge our understanding. Phenomena such as superposition and entanglement defy classical logic, raising fundamental questions about the very nature of reality. Are we merely scratching the surface of a deeper understanding? These gaps show us that no single discipline alone can unravel the entirety of the cosmos' intricacies. They remind us that science is not just about answering questions, but also about discovering better questions to ask. What complicates this further is the pervasive influence of instrumentalism. The idea that scientific theories are merely tools for predicting outcomes rather than explanations of reality. While practical in some regards, instrumentalism misses the point of deeper scientific inquiry. Prediction has value, no doubt, yet it's explanation that propels us forward. A theory that simply works is incomplete unless it also tells us why. Why do particles behave one way and not another? Why does evolution favor specific adaptations? Scientific progress thrives not on prediction alone, but on the explanations that unify phenomena across domains. Explanation is the true engine of knowledge. Humans have an innate drive not just to observe, but to understand. Explanations allow us to go beyond isolated observations, forging connections that unify what once seemed disparate. Through robust explanations, science overcomes its own limitations, transcending the accumulation of facts to offer clarity and coherence. The implications of pursuing such unified explanations are profound, especially for the future of knowledge. A true theory of everything won't focus solely on physics. It will integrate the explanatory power of all four strands. Doing so could revolutionize our understanding of everything, from consciousness to artificial intelligence to the very structure of existence. Imagine advances in quantum computation that push us closer to recreating human-level thought, or breakthroughs in evolution that deepen our grasp of how complexity arises in both biology and technology. The ripple effects would reshape what it means to know and to be. Ultimately, this unified framework, drawing together the strengths of quantum physics, epistemology, computation, and evolution, reveals a profound truth. The fabric of reality is not simply a patchwork, it is a magnificent whole. It bridges the gaps between disciplines, positions explanation over mere utility, and speaks to the compelling mystery of existence itself. While no single thread tells the whole story, their combination offers a vision far more complete and awe-inspiring than any could achieve alone. Understanding this fabric is not just about answering the how of our universe. It's about unlocking the why. And perhaps in doing so, it opens the door to what's next. The quest continues.